online, and you can finish writing those out. But I want to give you a picture of what those things are. Okay, so here is a picture of those things. And I'll give you two pictures here, but you recognize that the pictures are very similar. The radii, you see that those two blue lines are radii. They start at the center of our polygon, okay? And there's no circle there, but if I go to this slide here, you see the circle that is circumscribed around, right? That's what that definition was saying. So the center of that polygon there is the same as the center of the circle that's on the outside, okay? So those two blue lines are radii. And the angle that's formed in between them is what we refer to as the central angle, okay? Because that is a central angle, okay, for that circle as well. Does that make sense? If I look at those blue dotted lines, okay, two consecutive ones are a central angle, which is also then a central angle for the circle that's circumscribed around it. Okay. The red dotted line is our apophthegm, okay, which is a word that you haven't seen before, but it is simply defined as the distance from the center perpendicular to the base, or I guess the side of the polygon. Okay. Now in this section, we're talking about polygons. We're talking about regular polygons, meaning they have to be equilateral and they have to be equiangular. Equilateral and equiangular. Otherwise, the formula that we're going to generate here does not work. Okay. One thing I need you to understand is how many of those central angles are you going to be able to kind of implant inside this hexagon? How many of those central angles can you put in here?
8, 5, 6.
6. Okay. That's a central angle. That one's a central angle. That one's a central angle. Central angle, central angle, central angle. So you got 6 of them, right? Okay. Now we're going to go to the next slide to kind of prove the point here that I'm trying to make. What do you think your argument is about maybe that angle in comparison to, let's say, that one? They're the same, okay? And the logic for it, using what we've already talked about in maybe chapter 12, is that if this is a regular polygon, isn't that distance the same as that one? And those things are chords for your circles, right? And congruent chords had congruent arcs, and congruent arcs, working their way back inside, had congruent central angles. Does that make sense? So we've got 6 central angles here that are all the same. What should they all add up to? 360 degrees. So can you find one of those central angles by taking 360 divided by 6? Okay. What kind of triangle is that triangle there? Why is it isosceles? Okay, because these things here, okay, are radii, right? Okay, and they're congruent, so it's got to be isosceles. Now Chuck is saying it's equilateral. Why is it equilateral? Okay, so in this situation, you have an isosceles triangle where the central angle, or for the triangle, we call it the vertex angle. This is 60 degrees. So then that has to be 60, and that has to be 60. So this is a special case where that one is equilateral. Not all polygons is that going to be equilateral. So if it's a pentagon or an octagon, that triangle is not equilateral. But in all of them, in all regular polygons, that triangle is isosceles. Okay. Now that brings us to talk about the apophthegm, which is the segment that is it's in an isosceles triangle, and it goes from the vertex angle. Okay, the vertex angle is the one at the top up there, between the two legs that are congruent. And it's perpendicular to the base of the isosceles triangle. If you have a segment that does that, starts at a vertex angle, it's perpendicular to the base, what else does it do to the base? Cuts it in half. Okay? What else does it do to the vertex angle? Cuts it in half. Okay? And those two features are going to be extremely important for what we do in regards to finding these areas, because our goal ultimately is to look at that triangle right there. Everything that we can, or everything that we need to insert into our formula comes from that right triangle. Okay? So that's kind of the plan for today. Okay? Carter, do you have a question?
Yeah, what chapter are we on?
It's 10.3.
Why not 10.1?
Okay. All right, so what is, kind of the simple, maybe most kind of brute force way of finding the area of this polygon would be to find the area of maybe that triangle, then find the area of that triangle, and then maybe find the area of that triangle. And what are you going to do with all these areas? Add them up. Okay, so let's do that. I'm going to go 1/2. Now, some of you might say, well, all those triangles are the same, so let's just multiply by 6. And that's an approach. But I'm just going to do it this way. 1/2 base times height would be the area of this purple one, right? That's the formula for a triangle. Okay. For the light blue one, it'd be 1/2 BH. For the dark blue one, it'd be 1/2 BH. For these over here, these other three that I didn't color in, they'd be 1/2 BHs as well, right? All right, so do they all have 1/2 in them? All right, so that would be the area of that hexagon. I'm going to take a 1/2 out. Okay. Something else that we learned and that we saw in, or that we will see, I think, or I guess I did write up here in the definitions, is that this apothem right here is the same as that apothem, which is the same as that one. Okay. So those apothems are all the same. And in this case, they are the H for the individual triangles. Does that make sense? Okay. They're the altitudes. So I'm going to take that H out. So if I factor a 1/2 H out of this thing here, what are you left with? B. If you do that here, what are you left with? B. How many B's are you going to be left with? 6. Okay. Now let's look at our B's. So this was let me color them here. That was B, right, for that triangle. That was another B for that triangle. That was another B. That was the 4th one. That's the 5th B. And that's the 6th B. If I start at that B right there, and I add to it that one, and I add to it that one, and that one, and that one, and that one, what did I just come up with for that hexagon? Careful. Not the area. Well, yeah. Okay, base plus base plus base plus base plus base plus base of that hexagon is another way of saying perimeter. So let's just take that B plus B plus B plus B plus B plus B and write it as P. So you get 1/2 H times P. Okay. Now H, I don't want to refer to it as H anymore because it's not as descriptive of what we're going to kind of label segments here. We're going to call it A for apothem. And there is your formula for finding the area of a hexagon. Okay. At least one formula for finding the area of a hexagon. There are others. Okay. But why is that one nice? Because now, if I go to an octagon, everything stays the same. You just have 8 triangles, right? And you have 8 B's. Does that make sense? But would you still, if you add all those 8 B's up, do you still have the perimeter of an octagon? Yeah. Okay. So that formula is one formula for ultimately an infinite number of different regular polygons. You can use that to find the area of an equilateral triangle. You can use that to find the area of a square. You can use that to find the area of a pentagon, a hexagon, a heptagon, an octagon, okay, and all the way up as far as we need to go. Okay, 1/2 the apothem length times the perimeter. Okay. Now, what is difficult about these types of questions, and that people struggle with the most, is that there's going to be information that's hidden to you. Okay, and that's what happens throughout this entire unit of area and volume. Is it's not 7th and 8th grade area and volume anymore. Okay, the formulas are still the same. We might write them a little bit different, but for the most part, they're the same. But I'm not going to flat out tell you, hey, this is A and this is P, because that's just plugging in, right? They're going to be implied. They're going to be hidden. You're going to have to use your geometry facts, some of your algebra skills, to pull out the components of these formulas. And that's what people are struggling with in the past, because they forget information about special right triangles. They forget SOHCAHTOA. They forget Pythagorean theorem and that kind of stuff that allows them to kind of shed light on these implied measurements. Okay, so I think we'll get through maybe 2 examples here, get you a start on your homework. All right, so the process for doing this, okay, is you're always going to be, like I said, that little triangle, you're always going to be interested in that little triangle, okay? But you're usually going to maybe think about getting that little triangle from that there. Okay, that's an isosceles triangle, right? The number one thing we need is to determine this angle up here. Okay? You told me that there should be 6 of these triangles that can be drawn in here, right? Okay, 6 of these triangles. So how many degrees would that thing right there be? 60 degrees. You took 360 divided by 6, right? Okay. Now, I don't really, like I said earlier, I don't care about that triangle so much. I care more about that one. Okay. So what is this black angle here in comparison to the 60 that Chuck just gave us? It's half of it. And that's the relationship that this segment here, the apothem, bisects that central angle. Okay. So half of 60 is 30. Okay. So that angle is 30 degrees. And you're always, that's going to be one of the first things you're going to try to find with all these problems. Okay. And here is, if you want to draw that picture and go through that every time, that's fine. But here is a formula for finding half the central angle. Okay? The first thing you're going to do is you're going to take 360 degrees. Okay? And then you divided it by n, right? N being the number of sides of the polygon. So Chuck took 360 divided by 6, right? Got 60. Then you took half of that, right? Well, taking half of something is the same as multiplying by what? Multiplying by half. So if I multiply this by 1/2, it's going to put the 2 down here in the bottom. Okay? So there's my formula where n is the number of sides. Okay? And that will always give me 30. Think about this. How many sides does that figure up there have right now? 6. What's 2 times 6? 12. What's 360 divided by 12? 30. Okay. It gets me that angle a lot quicker than drawing the picture every single time. Okay? Now, if that's a fact, okay, and we need to find the area of the regular polygon, it's 1/2 apothem times perimeter. Always start with your formula. Sides. Should be an E there. All right, so we start with our formula and we start plugging in the things we know. Okay, do we know the apothem length yet? No. Okay, so I'm going to leave a spot there. I don't know that yet. Do I know the perimeter? Yes. Okay, now it's not explicit. You got to do a little bit of work, right? 15 times 6. Okay, 15 times 6 is 90. Okay, so put 90 there. Now that just tells me I got to find the apothem. Well, what's nice about this is if that side's 15, what is this side here? 15. So then going back to understanding that that apothem is the angle bisector, the vertex angle of an isosceles triangle. It does what to that 15 down here to make that distance right there? Cuts it in half. So if it's an odd number, we're just going to leave it as 15/2. Why do I leave it that way? Because it makes our math a little bit easier later on. It's just a 30, 60, 90 triangle now. Okay, so across from 30 is your n side, and across from 60 is your n radical 3 side, right? So I take my n value and multiply it by radical 3. And there's my apothem. That's lowercase a right there. Come up here, plug it in. 15 radical 3 all over 2. These are all fractions, right? Multiply straight across the top. So what you're going to do here is all these black numbers are rational numbers. They're all similar in their style and their behavior. So those are the ones that we multiply together. What's 1 times 15 times 90? What's 15 times 9? What's 15 times 10? 150. Minus then 15 would be 135. And multiplied by 10 would be 1350.
Yeah.
Okay? So 15 times 9 is 1350. And then I multiply by the radical 3. Leave it that way. 2 times 2 times 1 on the bottom is 4. They both are even, right? 1350 and the 4. So they're both divisible by 2. And there's my area. Okay? And it's units squared. The definition of area is the square area, I guess the square units that a figure encloses. The square units that a figure encloses. Now that's an exact answer. Okay, this is the logic here. Sometimes they want exact answers, sometimes they want decimal. Okay. Well, if I just set my mind to always wanting to find the exact answer, once I have the exact answer, is it as easy as just going to my calculator, typing it in to get the decimal? Okay. But if we work the other way around, if we work and go find the decimal first, you can't type the decimal in your calculator and then spit back the exact answer. Okay. So, yes, about 584.6 would be the decimal version of that answer. Okay. But we need the capabilities of leaving it as an exact answer because this class is meant and designed to help you develop skills and behaviors that are successful in other classes, right? You're going to want exact answers in other classes. You're going to be able to do that now. Okay, so we're going to practice it. Is that okay? You good? Okay, I thought you asked a question. All right, so let's quickly go through another example. It's a different shape, right?
Yes.
Same exact formula. Area equals 1/2 lowercase a capital P. Do we know one of those things?
Yes.
Yep. My apothem I don't know, but my perimeter is
40.
And because I know these are all going to be fractions, I just always write my perimeter over 1.
That's smart.
All right, so going through this then, if I look at, you're always, no matter what your shape is, 5 sides, 6 sides, 7 sides, 3 sides, 4 sides, doesn't matter, you're going to draw that triangle. Okay? It's going to be a right triangle. I need to know what this angle right here is. How did we say we found that angle?
360 divided by 5.
360 divided by
6, 5, 4, 7.
it was 2n. And n is your number of sides.
Get 2 in.
So 360 divided by 10. So that angle becomes 36 degrees. Okay. Now, can I use special right triangles with a 36 degree angle? Can I use special right triangles here? Okay. So if I can't use special right triangles, I have to use SOHCAHTOA. All right. Now, if I'm going to use SOHCAHTOA and I'm looking for the apothem here, I need to know one of these other two distances, right?
Yeah.
And one of those other two distances is hidden in that information. If the perimeter is 40, what is that side length right there? 8. So then what is that distance right there? 4. So now, the apothem is, to this 36, the apothem is the adjacent side, and the 4 is opposite. Okay? Which trig ratio uses opposite and adjacent?
No idea. No, tangent.
Okay, tangent uses opposite and adjacent. So I'm going to go tangent of 36 is equal to opposite over adjacent. A then ends up being 4 divided by tangent of 36. And that goes here. Okay. I think some of us are finding out the fact that when we don't pay attention prior, we get to situations where the information that we're trying to learn now is really, really hard to deal with because we don't have any prerequisite skills. Okay. So now I start multiplying. Numerators, 1, 4, and 40 gives me 160. 2 times tangent of 36 times 1 just gives me 2 tangent of 36. Okay. Remember, tangent of 36 is just a number. So we can actually take the 160 divided by the 2. It gives me 80 divided by tangent of 36. And that should end up being my area as an exact version, okay? Because there's no rounding in any of those numbers. That's the exact value of my area. Now, if I wanted to take it as a decimal, I type in 80 divided by tangent of 36, and I get 110.11. Now it'd be centimeters squared. Now, I know that's fast. There's a lot of information. Two examples, okay? You're going to see varying formats of those questions in your homework. They're going to flip-flop back and forth between hexagons and octagons and decagons and triangles and squares. When you're using these calculators, you're using the degrees. You got to make sure you're in the right mode, and that's something that you got to pay attention to on the course exam as well. But they're going to flip-flop back and forth between versions of these questions. They might start you with the perimeter, like these questions did. They might start you with an apothem, and you have to find the perimeter. They might start you with a side length, and you have to find the perimeter in the apothem. Okay? So they're going to start you with different components, but you should always be able to, using the geometry that we've learned throughout the year, you should always be able to work your way around to find A and capital P. Okay? We'll practice this a little bit more tomorrow. I've opened an assignment 10.3 on Math Excel. It is not due tomorrow. It will be due on Wednesday. Okay? But it's a good idea to start looking at that now. Maybe knock out the ones that you understand, the ones you can do. Then it'll give you an idea what you need to focus on in class tomorrow and discuss in class.
7 o'clock in the morning.